Well, good morning. This is 11:02 on Thursday morning, the 19th of October, 2017. It's supposed to be linear algebra class. The bad news is I'm the only one in the room, so hopefully some of the others will be coming in soon. Not too many announcements right now. Let me just hit a couple of things. If you weren't here on Tuesday to hear it, so I'm going to say it again in case you missed it on the YouTube, which, by the way, YouTube started off when I got this new loaner computer. It was just doing really fast. It was uploading well, doing stuff, then all of a sudden it went to a grinding halt or slowdown, and things are really behind in uploading now. So it seems to be catching up a little bit today, but boy, it's been behind for 2 days in a row. But anyway, that's done. Now, but starting this week, which is the beginning of the second mini-term, my office hours have been modified. Monday, Wednesday still the same, 3:15 to 5:15. Though yesterday I had to be on the Birmingham campus, so I was over there, not here. And then in a meeting most of the time. But then on Tuesday, Thursday, that's where the changes occurred. My office hours are now on Tuesday, Thursday. I didn't have any before except my lunch hour, 12:15 when this class was over with, until 1:15 when the first mini-term Physical Science 1 class met. But my Physical Science 2 class, because it has automotive students in it, they need it for their program. They are in their classes up until 3, so I can't start the Physical Science 2 class until 3:15. So therefore I have office hours from 1:15 to 3:15 that I didn't have the first mini-term. Well, where did those come from? Well, the fact that now I stay here till 8 o'clock on Tuesday, Thursday evening, whereas the first mini-term I was on campus until 6 o'clock. So that's where the hours went. Here later, so I can have office hours from 1:15 to 3:15, which will be today and later. Now, from now on. Here's an issue. I've got all the grading done so far. Everything that's been turned in all my classes, I'm up to date on grading. However, I'm behind in Blackboard, getting the grades on Blackboard from a number of reasons, but it's not going to get a lot better real soon. As soon as we get out of class today, I have a little bit of lunch, and then in those 2 hours office hours, the main thing I've got to do is get my second mini-term contracts done. Those are due today at 3, and so I've got to get them in today. When I finish that, I may have time to get a little bit of Blackboard done, but the other thing that's got to be done is spring schedule has to be completed. And that I don't know. I've either got to do it today or tomorrow, and whichever day I do it, I won't be entering grades. So whenever I can, I got to get the spring schedule done, and then I'll try to get those grades caught up. I got a few done in between the last 2 classes, but I've got so many it's going to take more than just a little bit here and there. All right. Trying to think if there's any other announcements. I can't think of any. So let's get started on linear algebra. We're in Chapter 2, Matrices, Section 2.4, Elementary Matrices, and we were at the bottom of page 80. It says, once you have obtained an LU factorization, and that's what we did last time, showed how to get that, of a matrix A, you can then solve the system of n linear equations in n variables. Has to be a square system, sort of. AX is equal to B very efficiently in 2 steps. Okay? And let me get my pen activated. Okay. Hopefully, yeah, that's done. All right. Here's the 2 steps. Here's what you're trying to solve. AX equal B. Now the book bolds, okay, the X and the B. Technically, that's because they are column vectors, and vectors are bolded. But I can't write bold, and so I write the vector symbol over it. Okay, sort of going around in a circle here. Okay, so if we're trying to solve that system of equation, it says it's very efficient to do this in 2 steps. Okay, here's what makes it very efficient. You've already determined the LU factorization. Okay, now that's not an efficient process, but if you've already gotten that done, you've already got the LU factorization, then this part gets pretty simple. Okay, now you know that. And you know that A is equal to LU, lower triangular matrix times the upper triangular matrix. You know that. That's what we did. Okay? Now, so you make up a new column vector, Y. Okay? Now, that column vector you're going to say is equal to the U, the upper triangular matrix, times X. That column vector. Okay? That gives you a value for Y. Okay? Now, from here, solve this. Do your lower column vector, lower triangular matrix times the Y, and set that equal to B. Okay? So take the upper triangular matrix, multiply that by X, that gives you a value Y. Take that, and on the left-hand side, multiply that by L, the lower triangular matrix, set that equal to B, and solve that for Y. Solve this for Y. And then the next step, solve UX for X. So this UX that you had here, which is equal to Y that you had here, okay, solve that for X. Solve this one for Y. Okay. Now, it almost feels like you're running around in circles. Okay? And you kind of are. Okay? Now it says here the column matrix X is the solution of the original system because AX is LUX, and LUX, UX is Y, and LY is B. Okay? So that's what I was sort of getting at before. AX, what you started with, is equal to LU times X, but UX is Y, so this is L times Y, and L sum Y is equal to B. Okay? That's the step line of thought. The second step here, going from UX to Y, is just back substitution. Because the U is the upper triangular matrix, the first step is similar, except that it starts, I'm sorry, I talk about these steps here. Step 1 and 2 here. Second step is back substitution. The first step is basically a back substitution, except it starts at the top of the matrix because L is the lower triangle. So they sometimes call that first step forward substitution and the second step back substitution, or whatever that's worth. Okay, so let's do example 7. Here is a system of equation. X1 minus 3x2 is equal to negative 5. x2 plus 3x3 is equal to negative 1, and 2x1 minus 10x2 plus 2x3 is equal to negative 20. Okay. Now, too bad we didn't have a chance. Neither of you have been here this week. This week, now that it's turned chillier, they haven't turned on any heat in the system. So the air that comes out is cold. It's cold outside. Before I started this class, I went over and checked the windows to see if opening the windows would warm the room up. It's just a little cooler outside than it is inside, so that would have just made it colder. But the air handling system is not putting out any heat at all. It's only either recirculating the ambient air, which is cool, or it's actually chilling it a little bit, which is not good either. So the room is cold, I'm cold, my head's stopped up, my hands are cold, I can hardly talk. It's been miserable. First class wasn't bad because we didn't have the system on until 8 o'clock. So the building had just sort of was okay overnight, okay? Just the heat of the building was not bad. Then they turned on the system, but I also had a room full of students, and so it kept the room comfortable. But my second class, about half the class or more were absent, so it was really cold in here, and it hasn't gotten any better. It is warming up a little outside, which makes it not quite as bad, but it's still hard to mess with. Okay, that was why I'm sounding so bad. And also maybe why I'll have to, if I have to stop just to go get something warm, I may have to do that, but I think we're okay. All right, here's our system, okay? Now, if we were to write this as a matrix equation, basically, your A would be your coefficient matrix, which is 1, negative 3, 0, okay, just a coefficient matrix, 0, 1, 3, and 2, negative 10, 2, okay? Now, if you look back to example 6, the last one we did last time, you'll see we started with this matrix right here. 1, negative 3, 0, 0, 1, 3, 2, negative 10, 2. Okay? And we row reduced it to get it to an upper triangular form, keeping up with the elementary matrices that produce that, took the inverse of those matrices, multiplied those together in the reverse order, and we came up with the lower triangular matrix. So we've already got our upper and lower triangular matrix for this matrix, and they would be this from the last time. And we always do it in the order LU, okay, lower, upper, okay, LU factorization, Lulu, whatever you want to remember it by, always have it in that order. So your lower triangular matrix for this one from last time, trying to find, there it is, 1, 0, 0, 0, 1, 0, 2, negative 4, 1. Okay, that's the lower triangular matrix for matrix A. The upper triangular matrix for matrix A, which is the first one we got, was 1, negative 3, 0. 0, 1, 3, and 0, 0, 14. All right. Now, let me say this. Remember our process of going from A, we went to U first, even though we list L first. We went to U first. What we did row reduction. Get it in row echelon form. Not reduce row echelon form. We just did row reduction. And that came out with our upper triangular matrix. Okay. In doing that, okay, it made the first two elements of the diagonal both ones. That's part of the process. Okay. There is an issue with that. That's why I'm bringing it up now. Trying to find where it stated it. I know it stated it. I guess it was okay. I can't see it right now. There it is. I think it is. If U can be obtained from A using only the row operation of adding a multiple of one row to another row below, then the matrix L is lower triangular with ones along the diagonal. That's the lower triangular matrix. This one. I mean, the first one there. If you got that. If you could not be obtained that way, the upper one, and notice the upper one doesn't necessarily have ones on the diagonal. It has ones on the first two, but not on the third one. Okay? But the lower triangle, if, and I believe it's only if, you got your row reduction that you did there in the upper only using multiples of one row times another. You didn't have to multiply a row by a fraction form, or you had a fractional form, so you multiply it by something. If you didn't have to do that, that produced a lower triangle matrix with ones in the diagonal, even though your upper triangle wasn't totally ones in diagonal. Okay. So that's just a little aside. So don't always expect them to come out this way, but they did state that before. Not that it really matters any now. Okay. So what do we do with this? All right. What we want to do is come up with a column vector y that is u times x. Okay? All right. So let's write down u times x. I'm sorry, u times All right. They don't seem to be following their steps too well. They say first let y equal ux, but they don't write it down, okay? And I guess there's no real reason to. Okay, but I'm going to write it down. Again, the u is this one. Remember, this is u, this is L. Okay? So, ux would be 1, negative 3, 0, 0, 1, 3, 0, 0, 14 times x1, x2, x3. Okay. They didn't require you to do that, but they said let that be. Okay. So this is what we're calling y. Okay. Now it doesn't look much like a y, does it? If you multiplied that out, you would have x1 minus 3x2 would be your top entry. X2 plus 3, x3 would be your second entry. And 14, x3 would be your third entry. Okay. So, but again, they didn't even write that down, but I did for future reference. Okay. That's your u x equal y. Okay. Now, it says solve the system Ly equal b for y. Okay. Well, your L is your lower triangular matrix. So this system would be 1, 0, 0, 0, 1, 0, 2, negative 4, 1. Okay. I'm having trouble keeping that thing up. Okay. That's your lower triangular. Your y vector is y1, y2, y3. Everything's three-dimensional here. Okay? And B we already know. Negative 5, negative 1, negative 20. Okay. Not too neat there. Okay. Trying to get that to look a little better. Okay. Can't get my pen back. There we go. All right. I've been fighting it, but I'm going to have to pause for just a minute here and go get something to drink because my head is just totally clogged up and I can hardly breathe. So sorry about this. The room is just so cold. Okay, I'm back. I also did this time open the windows. It felt like it was about the same temperature outside, maybe a little bit warmer. The day is warming up. It's supposed to get up to 77 today. I don't think we're anywhere close to that now, but I do believe it's probably a little warmer outside than in. So I opened the window. I don't know if there'll be enough time for that to make a difference or not, because there's not a lot of temperature change difference here. Okay, but here we have from up here, this is our y. But we didn't do anything with it. It's just up there. This is what we're doing with that y. We're multiplied by the lower triangular matrix. And this basically is our back substitution. Forward substitution. We have here that y1 is equal to -5. You can see that by that multiplication. So we got y1 equal -5. All right? And then also it just happens to give you y2 is equal to -1. So this is pretty easy so far, -1. Okay? And then the third one, multiplication here, is 2y1, which is 2 times -5. Well, I'll write it down. 2y1 minus 4y2 plus y3 is equal to -20. Well, 2y1 is -10. Minus 4y2 would be plus 4. Plus y3 is equal to -20. Okay? Now, if we add -10 and 4, you get -6. Add 6 to both sides, and that gives you y3 is equal to -14. Okay? So now you have your three values for y. You have that y vector. Okay? And it's -5, -1, -14. Okay? I haven't written it very neatly because I don't have room for it. Okay, so now with that, we can go back and do our back substitution up above. So, since we've already written down both of these, I think I can erase them here. Okay. All right. So what we have now is writing this over with what we now know is 1, -3, 0, 0, 1, 3, 0, 0, 14 times x1, x2, x3 is equal to the y we just calculated, which is -5, -1, -20. All right. Okay. Now, sorry I don't have much room. This was one advantage when we were doing it on the board. You just couldn't record it. But doing it on the board, I could take up the whole board to work the problem. Right now, this loaner computer has a smaller screen than what my older one did, and then it's restricting me to even a smaller box here. So even though it might look like to you I'm writing bigger, I'm not. I'm writing smaller, but the projection of it is bigger. Okay? So, I don't think I need the bottom part of this anymore because we've already placed it everywhere we need it. So I'm going to have to erase it to get in the next step. Okay. Okay, so that was our forward substitution, or what they call it. Okay, finally that erased. Yesterday it took even longer than that. So now let's do the back substitution. I think, I wrote it right. No, I didn't. I looked at the wrong thing here. This isn't minus 20, it's minus 14. I erased it, but I'm pretty sure I got it right now. Minus 5, minus 1, minus 14. Okay. Now, doing back substitution, 14x is equal to minus 14. So that means, x3. So that means x3 is equal to negative 1. Then doing the next one, x2 plus 3, x3 is equal to negative 1. Well, x3 is negative 1, so it's x2 minus 3 is equal to negative 1. This gives us the x2, add 3 to both sides, is equal to 2. Now with x2 and x3, we can do the top row, which is x1 minus 3x2 plus 0 is equal to negative 5. So this will be x1 minus 6 is equal to negative 5. Add 6 to both sides, you get x1 is equal to 1. Okay, so now we have solved this. It's 1, 2, negative 1. That's our x column vector. Okay, and that finishes 2.4. And right now, either the wind has shifted or something. It's now getting colder in here, so I'm going to close the windows now. Sorry about this. This is just driving me nuts. All right. So that finished 2.4. Let's talk about the exercises here. And remember, this text, this author, has this www.calcchat.com, has worked out solutions for the odd number exercises. They have the answers for odd numbers in the back, but they also, if you can't get the answer, can't figure out how you're getting it wrong, you can always go to www.calcchat.com to see the worked out solutions to these odd number exercises. Well, hey, good to have somebody in here. All right. Come over here. And so far, adjustments. Okay. Let me get things switched around here. I have done everything I can to try to warm up the room, and I can't do anything. It's about the same temperature outside, or maybe a little cooler than in here. They don't have any heat in the system. It's all just blowing either ambient air or cold air. So I just finished doing example 7 on page 81. So that finished 2.4. Here are the homework exercises. What I was just saying is, the computer is blowing out, the fan is blowing out the heat, and I'm trying to hold my hands in the book and everything right there where I can get a little bit of heat. I assigned the odd number exercises for 2 reasons. Number one, their answers are in the back, so you can check your answers, see if you got it right. If you did, go on. If you did get it right and you can't go back and figure out how you missed it, then you notice that each exercise set, it says, see www.calcchat.com for worked out solutions to the odd number exercises. So you can go to that website and see the actual worked out solutions. So if you can't get the answers in the back, go to calcchat.com. So do any of the odds 1 through 7. I think I assigned these before. Either 9 or 11, either 13 or 15, or both, all of those. Any of the odds 17 to 21, either 23 or 25 or both. Any of the odds 27 to 33. And then they have a couple true false. 35 should have the answer in the back, and maybe at calccheck.com. I have to check that. 37 is a writing exercise, so I doubt if they'll have that either in the back of the book or at CalCheck, but they may talk about it. 39 should be back there, so do that one. Either 41 or 43 or both. Do number 45. It's one very similar to the one I just did on the homework, from the example. And then 47 is another writing exercise. Now, this is one of the things that bugs me. It's a pretty good text, I think. This is one thing that kind of bugs me, and it seems like a lot of texts do this. Example 49. Not in the text, exercise 49, in the homework. Rather than being in the text, they're giving you a new definition. It's determine whether a matrix is, and I don't even know how to pronounce this, idempotent, huh?
What section is this?
This is 2.4. Yeah, this is the homework exercises for it. 49 through 40 through 52. So you do either 49 or 51 or both. But they give you a definition. Determine whether the matrix is idempotent or idempotent or something. I don't know how you pronounce it. A square matrix A is idempotent, I guess is how you say it, when A squared is equal to A. That's the definition. Why wouldn't they give you that in the text? They're giving it to you here. And it says determine whether these two are 49 and 51. Okay? And what you have to do is just multiply it by itself, see if you get the same thing you had to begin with. Okay. Then 53 is another one similar to that. So do 53. And then 55, 57, 59 are all proofs. So you can do as much or as little of those as you want. I don't know how much the answers will be in the back. I don't know how much they go over on calccheck.com, but you can review that. All right, so that finishes 2.4. Let's move on to 2.5. Okay? And since I don't have PowerPoint, I'm doing it on PowerPoint, but I don't have it provided, so I'll just go to a clean page. Now, we're not going to do much of 2.5. We may not do anything. They talk about here stochastic matrices, and there's nothing in the course description that indicates we have to do anything with this. So I think we're going to skip the whole section. I just wanted to thumb through it to see if there's anything that really you needed in here. And so far, I would say no. There are some very interesting things in here, but we're going to skip this whole one. So we're not going to do 2.5. If your field of study has you doing things like stochastic matrices or things like this, this is where you'll find out about it. But there's nothing in the course description that requires us to do this. So since we do need to move along, we do that. Now, there are some consumer preferences, so there's some really good examples of how you can use some of this stuff. So I would say if this is of interest to you, take a look at it. There's a section in here on cryptography. Okay? I don't know if you saw the movie No, it was a PBS show. Oh boy, I can't remember its name. But it basically was how the British broke the German code. I think it was called the Enigma Code in World War II. And basically, that was a big part for the Allied forces beating the Axis forces. If the Brits had not broken that code, Germany would have had a lot more successes. But what they did, and this is really bizarre, they broke the code but didn't tell anyone they broke the code. I don't even think they told their allies, like us or friends, that they broke the code. They just used the information to their advantage. Even times when it cost dozens, hundreds, or maybe even thousands of lives that could have been avoided, but if they had done the avoidance, then Germany would have realized they had broken the code and they would have changed codes. So they thought it was more beneficial to sacrifice some lives and ultimately win the war. So lose a few battles but ultimately win the war. Whereas before, they would have won those battles, but Germany might have won the war. So it was really a tough call. So if you're interested in cryptography, then there's a section in here for you. Even if you don't go into detail, it would be a decent paper topic as well. Okay? And then there's this Leontief input-output models. And evidently this guy, Leontief, whoever he was, came up with this. And it's not a particularly awe-inspiring model in my mind. It's very tedious, and I don't personally see that much use for it, but all the books focus on it. So evidently it's classic in some nature. I just haven't seen the beauty of it. If you're interested in who in the world Leontief was, you can write a paper on him. How he developed this model, you can do that. You know, he may have even won a Nobel for it. I don't know. But if you're interested in that. Now, the last thing done in this section is least squares regression analysis. This is really a handy tool in statistics. Okay? In fact, most of this section has some sort of tie to statistics. And least squares regression analysis is a very handy tool when you're estimating. Okay? It's a great topic to look at. We just don't have time to do it. But you can look at it there. Everything is there for you. So that's 2.5. Chapter 2 review exercises are here. Again, the odd number exercises have answers in the back and worked out solutions at calcchat.com. So you can do any of the odds 1 through 5, 7 or 9, 11 or 13, 15 or 17, any of the odds 19 to 25, 27, 29, 31, either 33 or 35, 37, 39, 41, okay, 43, 45, 47, okay, and then after that, 49, yeah, 49. After that, those are the ones from that last section, 2.5. You don't have to do those unless you just want to do them. I think. It could be the first few of those you might be able to do otherwise. But I know from 57 on are from that last section. So that ends chapter 2. Now let me see, I can't remember if I have your test made up or not. I know I have them made up, whether I had copies made or not. Let me see if I can find those. Well, yeah, I have one. Oh, this looks like my original. Can't tell which is my original. Okay, I think that is. Whichever, I don't have the copies made yet. I don't know if this looks like the one. All right. So what I'll do, right at the end of class, I'll go down and make 2 copies and give you one. So you have something to do right at that. You have to leave right at the end?
I don't know.
Okay. So it won't take me long.
All right, no problem.
Okay.
That's the new fit.
What's that?
That's the new fit.
Yeah, that's test 2.
Okay.
Okay. So,
Oh, this is the first day you passing it up?
what's that?
And I said, this is the first day you passing it up?
Yeah. I don't even have copies made yet. So let's move on to chapter 3. Now, chapter 3 is the shortest chapter we're going to do. So it's not going to take us long. I think you'll find it's probably the easiest chapter we're going to do. So it's on determinants. Okay? We've already touched on determinants when we were doing inverse of 2x2 matrices, remember? Okay, we're going to go a lot more into detail here. And we're going to start with the determinant of a 2x2 matrix, which I think you already know, but let's hit it again. Every square matrix can be associated with a real number called its determinant. No imaginary number, a real number called its determinant. Historically, the use of determinants arose from the recognition of some special patterns that occurred in solutions of linear equations. So, I'll try to do this quickly. I don't do very many things quickly. But if you had this A11x1 plus A12x2 is equal to some B1. And A21 x1 plus A22 x2 is equal to B2. Okay? Now, if we were going to solve for x1, what we would do would be eliminate x2. I don't know if you remember this from solving a 2x2 system by elimination. You would multiply the top equation by negative A22 and multiply the bottom equation by, and add the two together, and multiply the, let's see, let me make sure. Now, let's multiply the top equation by plus A22, the bottom equation by negative A12. Okay? Now, you could do it either way, but I'm going to do it this way to make it look like what they have in the book. All right? So, what that gives you is A11, A22, x1 plus A12, A22, x2 equal A22B1. Okay? The second equation is going to be negative A12, A21, x1 minus A12, A22, x2 equal to a minus A12, B2. All right? Multiply the top equation by A22, every entry. Multiply the bottom equation by negative A12. The reason we did that makes this one, this coefficient, and this one the opposite of that coefficient. A12, A22, this is plus, this is minus, add these two together, you eliminate your x2's. Okay? So therefore you can solve for x1. Okay? I'll write it out. A11, A22, x1 minus A12, A21, x1 is equal to, because these go to 0, A22, B1 minus A12, B2. Okay? Well, here you have common x1, so factor out the x1, and what you have left is A11, A22 minus A12, A21 is equal to this stuff, A22, B1 minus A12, B2. Divide both sides of the equation by this, A11, A22 minus A12, A21. A11, A22 minus A12, A21. Okay, this goes out. So there's your x1. A22, B1 minus A12, B2 over A11, A22 minus A12, A21. I am so hungry I can hardly stand it. Okay. Look. All right. So there. That's your x1. Now we could do the same with x2, eliminating x1. This time, make sure I do it the same way they do. multiply the top equation by minus A21 and the bottom equation by positive A11. So that will give you opposites here and that. Now, it'll take up another whole screen here to do that. So I'm just going to write the result. If you did that, multiply the top equation by A21 and the bottom equation by, no, top equation by minus A21, bottom equation by positive A11. That's it. Okay. Do the whole thing through and do that. Here's what X2 would come out be. Okay. Just I want to make sure I got the other one right before I write this one down. Yes. The X2 would have been, I'm not going to do all the gory detail here, A11B2 minus A21B1 divided by A11, A22 minus A12, A21. Okay. Now, hopefully, the first thing that pops out at you there is that the denominators are exactly the same. Okay. The next thing I want to pop out to you, at you, you note, or whatever, is that if you think back of what we were doing before with the determinant of the 2 by 2 matrix, it was this times this minus that times that, which is exactly what your denominator is in both of those. That's the determinant of the coefficient matrix. Whoa. Okay? Second thing to note is that what your numerator is, if you're solving for x1, then put your b1 and b2 here, and then do the determinant here, and you get b1 a22 minus b2 a21, b12, I'm sorry. And that's your determinant there. If you're solving for x2, put your b1 and b2 here, and you have a11 b2 minus a21 b1. So, for what it's worth, on a 2 by 2 matrix, if you want to solve these, all you have is your solution, x1, is your determinant of your coefficient of your determinant with the constants replacing the coefficients for x1, the determinant of that matrix divided by the determinant of the coefficient matrix, and over here, the determinant when you replace the coefficients of x2 with your constants b1 and b2, that determinant divided by your determinant coefficient matrix. Oh wow, okay? And by the way, we're going to hit it later, this is Kramer's rule. This is how you can solve any system 2 by 2 equations using determinants. Okay? Now, the thing is, calculating the determinants are pretty easy to do, but you could probably solve this a lot easier without doing it, okay? So it doesn't really say you much, but on the other hand, this is something that can be programmed to be done very quickly and fairly easily. So for computer purposes, this may be a better way to go. Okay. So here is the definition of the determinant of a matrix. That's why we do it here's the definition, if I can get my cursor to move right. All right? The determinant of a matrix, this is a 2 by 2 matrix. Matrix A is A11, A12. Remember, the first entry says your row, second entry says your column. A21, A22. The determinant of that is given by, and there's several different expressions for it. You can say DET of A. You can do flat bars A that looks like absolute value, but matrices don't have absolute values. They do have determinants. Okay? You could also do it this way. A11, A12, A21, A22, and rather than putting brackets around it, put straight bars, and that means take a determinant. But here's what the determinant is. No matter how you write it, here's what the determinant is. The cross product, you might say A11, A12, in other words, the main diagonal, the product of the main diagonal elements minus the product of the off-diagonal elements. Okay? A12, A21. Okay? That is your determinant. And it doesn't matter which one. What's that? Oh, no. I wrote the first one wrong. Sorry. I think you caught me. That's A22. It's A11, A22 minus A12, A21. Okay? Product minus the other product. Okay? So, let's do a few of those. Go clear my screen here. Still cold, but I feel like I'm warming up some. Of course, I think what I'm doing is holding my hands up for this fan. Okay, so let's do these. These are pretty easy to do. Here's matrix A. 2, -3, 1, 2. What's the determinant of A? What would it be? Yeah.
2, 3.
Determinant. Multiply. The cross product here. 2 times 2, 4, minus
3.
Minus a -3. Okay? So that would be 7. Perfect. Okay? Here is B. Another 2 by 2. 2, 1. 4, 2. Find the determinant of B.
2 times 2 is
4.
Minus 4, which is 0.
0. Very good. Here's C. C is 0, 3 halves, 2, 4. What's the determinant of B? Let's see.
All right, now 0 minus 3.
Right? So that's equal to -3. All right, good deal. Caught on to that very nicely. 2 by 2s are easy. Really easy. Very nice. Okay? However, when you get bigger matrices, they get a lot more complicated. Okay? So, now the book goes into defining these things called minors and cofactors. And frankly, I have the worst trouble remembering what they are and why they call them what they do. But using them is pretty simple. Okay? So let's get the definitions, but then after a while when you really use them, if you're like me, you'll forget the definition and just use them, okay? To define the determinant of a square matrix of order higher than 2, 3 by 3, 4 by 4, remember you can't do a determinant on a rectangular matrix. It's got to be square, okay? Now, I meant to point out something before. 2 of those had determinants that were not 0. One of them had a determinant of 0. We'll learn later that if the determinant of a matrix is 0, that means it's not invertible. You cannot take the inverse of it. If it's non-zero, you always can take the inverse of it. Okay, so we'll see that in some other features later. All right. So I think all we're going to have time is to define these things. So if A is a square matrix, okay, then the minor, and we're going to have it being 3 or greater, n by n, where n is 3 or larger. Okay, then the minor m sub ij of the entry aij is the determinant of the matrix obtained by deleting the ith row and the jth column. Okay? Of A. Now the cofactor, that's the minor. Cofactor Cij of the entry Aij is -1 raised to the a plus j. This is really a difficult way to do it, but it works, times the minor ij. Okay? Now, let's do a quick example. A is a 3 by 3 matrix. A11, A12, A13. A21, A22, A23, A31, A33, hey, yuck, 3-2. In a rush. I always do stupid things when I'm in a rush. I can't get my pen to come up, the eraser to come up. Erase the wrong one. And A33. All right, there's your matrix. Give me a pair of numbers.
Is that random?
Both of them need to be between 1 and 3, including either 1 or 3.
There's 3 of them?
Yeah.
1, 2, 3.
No, just give me 2. A pair, yeah.
1 and 2.
1 and 2. Okay? For the entry 1, 2, A12, wipe out the second column and the first row.
All right.
Okay, the minor for this matrix A would then be M12 would be A21. It's also a matrix. A23, A31, A33. Okay, that's the minor. Okay, I'm sorry. Right. Wait, I said it's a matrix. It's not a matrix. It's the determinant. Yuck. It's the determinant of the matrix. That's the minor. Okay? Now, the cofactor of 1, 2 is that minor multiplied. Hey, can't have. Okay, say that one more time. On Monday and Wednesday, yeah. Yeah, yeah. Yeah, he has his afternoon and evening class here. What's that? This classroom, right. 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 That would be great, yeah.
I know on the schedule it said he used that room 2.
Right.
We could go right there only, and I can move him
right
there.
Right.
Okay.
You see, earlier in the term when it was not sure if I was going to teach one of those classes or not, if they got big enough, then I would be here and he would be there.
Okay.
Okay. But then when both of them were small, we combined them. And then since I let him use my computer, he just came in here.
Okay.
I didn't have any classes after that,
right.
So he just came here.
Right.
Now, there was a portion of the term when the math team would meet here, and then he went back to using that room.
Okay.
But the math team thing's over with now for at least the rest of this term. So he'll stay in here, and that room will be open.
Okay. Okay. That's all I want to know.
Right.
Thank you.
Glad to. No problem. All right. Now, what the cofactor is just multiplying this probably plus or minus 1. And how do you determine that? Well, what they say here is to add 1 and 2 together, and that gives you 3. And -1 to the third power would be negative. So the cofactor would be negative the determinant. Okay? A21, A13 minus A23, A31. Okay? It would be the opposite of that.
A21, A33?
Well, yeah. You see, the minor is that determinant. A21 times A33 minus A23 times A. Yeah. That is the minor.
Okay.
And then the cofactor is, in this case, negated, because you add the I and J together, 2 and 1 together to get an odd number, it's going to be the negative.
I'm saying you had wrote A21, A13.
A21, oh, 33.
Yeah.
That's supposed to be 33. I'm sorry, I see what you mean. 33. I think I tried to write it, but the pen didn't write.
You said negative, right?
Yeah.
Okay.
The cofactor makes it negative because all you do is do -1 to that power. Since you chose 1, 2, that's an odd number, so it's going to be negative. Now, you want to see the easy way to do this?
It don't matter.
Okay. Look at your matrix to begin with.
Alright.
Okay. Always start with plus. Plus, minus, plus, minus, plus, minus, plus, minus, plus. You get the cofactor to get that. Or plus, minus, plus, minus, plus, minus, plus, minus, plus. As long as you go in an orderly fashion,
Yeah.
and just go either horizontal or vertical, plus, minus, plus, minus, plus, minus, plus, minus, plus. It all stays the same. All these are pluses.
Okay.
Yeah.
I got it.
Yeah. So rather than doing that, I just figure out if there's a positive position or a negative position. Okay. So that's even.
Yeah.
Okay. But the minor is the determinant when you wipe out the row and column. That's it. And then the cofactor just gives a sign to it. Plus, minus, plus, minus, plus, minus, plus, minus. Yeah. So, all right. So we'll pick up next time with example 2. We'll actually do one. Got too much. All right, good deal. Okay. And let's see, homework exercises. I don't know, there's probably not many you can do. Yeah, you can do any of the odds 1 through 11. Try to do 13 and or 15. If you can't, we'll do an example of that next time. Okay, good deal.